You should have papers for me. Chapter 1, Section 1. Send it to your left. If you are pulling stuff from a spiral notebook, please take the little fringy edges off your page. Just put your name on each one and I'll see it. Okay. I would like to know when two distinct propositions mean the same thing. We've already seen this in our discussion of converse and inverse and contrapositive in the original conditional statement. And what I was looking at is I was looking to see if they gave me the same results on a truth table for all the cases. And we'll refer to this as logical equivalence. Now, compound proposition means there are ands, ors, nots, arrows, parentheses, whatever is needed. It's not just a single letter. But a single letter as a simple proposition could still be considered as, is this equivalent to something? I need two terminology statements, well, two definitions here. Remember, our compound propositions are simple propositional variables connected with all of these operations. If my result is always true, I build out the entire truth table and the rightmost last column is always true, we're going to call that a tautology. Tautology, a tautology. I can change one word in this definition from always true to always false. And then instead of a tautology, we'll use the word contradiction. But we saw lots of truth tables where the final result was something in between. So if it's a mix of these, is called a contingent proposition or a contingency. So if I give you a statement, you should be able to tell me what's going to be always true, always false, or something in the middle by building me a truth table. Yes? Shakespeare. P or not P. To be or not to be, right? No, I just used one P. Is this a tautology, a contingency, or a contradiction? I only have one propositional variable involved. So I need to build a truth table that starts with just those options and then builds from that everything I need. Negation simply flips the bits. So things that were false are now true, things that were true are now false. We simply flip the values. Now, or. When is or true? When is or false?
One of them is true, but the other is false.
That's our exclusive or. Is this the exclusive or the inclusive or? Inclusive. So not only is that allowed, but it's also allowed if both of them are true. The only time or is false is when both are false. When it's our exclusive, that's a different story. This is the inclusive. So one of them is true, one of them is true. This is a tautology. The result was an always true statement. Imagine, if you will, walking into a room with a light bulb and two switches. When is the light bulb on? When is the light bulb off? In this case, regardless of which switch is up, which switch is down, the light bulb stays on. Because it's really the same switch. When I flick that one up, this one goes down automatically because it's the opposite position. What about that statement?
Well, I guess it would be P and not to be.
P and not P. I'm not doing Shakespeare this time, but yes. Okay. What's the truth table result out of this one? Exactly. I'm going to start with the same two columns here. But when I'm using and, for and to be true, both of the individual components must be true. T and F, nope. F and T, nope. This is a contradictory statement. These were simple. Each of the two pieces involved here were very simple. But I can have a really big expression. Something like this. But instead of just looking at one thing, remember, I said at the beginning, two propositions are equivalent if they generate the same truth tables. I want to compare this proposition with this one. So, the first thing I said was that two compound propositions are equivalent if they give me the same truth table. There's another way to think of this. Here's another definition. I've already used P and Q up here, so I'm going to call my compound propositions R and S for the moment. Two compound propositions R and S are logically equivalent when R, if and only if S, is a tautology. So instead of building two separate truth tables and comparing them, I build one truth table for a bigger statement. So if I want to compare these two things that are written at the top of my page, call the one on the left R, call the one on the right S, what I really want to look at one statement looks like this. And what I want, when all is said and done, is every row to be a true. Because that's what a tautology means, to be a true. So my question to you is, are these two things logically equivalent? I need to build a truth table for this. There are only two variables in this. How many rows do I need in my table? 4. And we've seen them before. P, Q. Now you have your choice. You can start with the thing on the left side of the if and only if. You can start with the thing on the right side of the if and only if. We're going to have to build both of those, and then we're going to have to put the bidirectional arrow in the middle and build one more column. So, you want to do the thing on the left first or the thing on the right first? Left it is. The left says not P or Q. Parentheses tell me I need to do the or before the not, otherwise my order of operations would be different. So the first thing I do is I do P or Q. Fill in that column. Because it's an or is only false. The inclusive or is only false when both terms are false. To finish out the left-hand side, I negate this. Since that's my left-hand side, I'm going to remember that this is one of the columns I want to work with at the end. So I'm going to write LHS, left-hand side, top of that column. So far, so good? This is all the stuff we did previously. I'm just doing more of it. Now I need to build the right-hand side. Starting with the same P and Q in the same order. That's why I've covered up these columns, so I don't look at them at the moment. I'm building the right side. The right side starts with not P, not Q. So I need a not P column. I need a not Q column. I've finished the left-hand side. I can put it out of my mind for the moment. What's my not P column look like? False, false, true, true. my not Q column and then I AND those together. Yes? AND. Notice now, I don't even have to look here. The AND only refers to these two columns. So everything else that come before those is irrelevant at the moment. AND is true when, false when.
True, false, false, false.
AND is true when both of the component pieces are true. Both of the component pieces are only true here, so it's going to be false on all of the rest of them. These two columns are not in the quote-unquote standard order, so I have to go through them one at a time. This is our right-hand side. Yes? So now I need to do the very last part of this, which is to compare left-hand side if and only if right-hand side. And rather than write out all the damn symbols all over again, I'm just going to write LHS and RHS. But now I'm just comparing these two columns with my if and only if statement. So I need to go back to Friday, which is where we did if and only if. When is if and only if true? When is if and only if false? It's what when they're the same? It's true when they're the same. They're the same here. They're the same here. They're the same here. They're the same here. This is a tautology. Now I can be sneaky and I can say, hey, wait a minute. I knew these were going to be equivalent when they generate the same truth table. Yes? So really, when I compare this column and I see that they're the same, I know this is true. If I want to be pedantic, I should actually check that I got all truths at the end. But as soon as those two columns are equal, and Brandon is right, if and only if is true when they're the same, I can short circuit that last step. Do I want you to short circuit that last step? Only if you write something like this that says, hey, look, these are the same. That's good enough. So, as a conclusion, not parentheses P or Q is the same thing as not P and not Q. Remember, that triple bar equal sign is the logical version of an equal sign. That's logical equivalence. This particular result kind of looks like an algebra result to me. Negation. Think of this kind of like a minus sign, right? A switch from positive to negative. And I got rid of the parentheses. There's a name for that rule. Distributive rule. There's just one problem. When I distribute, the sign in the middle doesn't change. And here, I move the minuses from the outside to the inside. I switched this. This actual rule was discovered by a gentleman by the name of Augustus de Morgan and is called de Morgan's law. This is actually version 1 because there is a version 2. And it turns out there are a lot of logical equivalences that relate to our arithmetic ideas. And if we think about this kind of like I talked about bits and ones and zeros, and then and became multiplying. There is an arithmetic hiding under here. I am right now going to guarantee you that there is a giant list that I have not memorized, and I doubt I ever will memorize. And I don't want you to memorize it either. On page 29 in the textbook, tables 6, 7, and 8, all about logical equivalences. Holy crap, that's a lot of stuff. But if I take a look at this start of table 6, here's our De Morgan's law right here. And the version we did, the or on the inside became an and. Here, the and on the inside becomes an or. So when I switch all of the true and false statements, I switch the logical connective as well. You'll notice there's nothing up here about distributing knots. There are 2 rules titled distributive rules, but they're about distributing or over and over or. One of the sentences y'all did for homework was about if you miss the final, if you get the flu, you won't pass the class, that sort of thing. One of those came out and it was 2 if-then statements, right? If you get the flu, you won't pass the class, and if you miss the final, you won't pass the class. Here's a distributive rule with an arrow on it. If you get the flu, then you won't pass the class. And if you get the flu, then you'll miss the final. So if you get the flu, you'll miss the final and not pass. I do that in English all the damn time, don't I? Pull one condition in front of 2 consequences, or 2 different conditions in front of the same consequence. If I get the flu, then I won't pass the class. If I miss the final, then I won't pass the class. If you get the flu or miss the final, then you won't pass. Here, wait, this was an and, that became an or. Because either one of the conditions gives me the same consequence. This table, you should, if you've got an electronic version of the book, put a bookmark on this. If you've got a physical copy, put a bookmark in this page. Now, the one I actually like the most in here is this one right here. It turns an if-then sentence into nots and ors. Why is this beneficial to me? It's beneficial to me because there's no circuit for if-then. There's no logic gate for if-then. But there are logic gates for not. There are logic gates for or. This is how I can get a computer to do an if-then sentence. Even if you're writing in a high-level programming language, you have to compile that sucker. Your compiler turns this into that. This is what it tells the computer to do. I believe that you should take a look at that piece of that page fairly closely. We're going to use it frequently, but I'm also going to end up with sentences that I want you to check. Now, I'm in the same boat here as I was before I looked at page 28, before I looked at these tables. I could try and go through all the tables and figure out, can I use this rule? Can I use this rule? Can I mix and match this? I think that's much harder to do. So in spite of having all of those rules, I tend not to do them as much as one might think. I'll show you a reason to do them a little later. But if I'm given a sentence like this and I'm asked, are these equivalent? My default procedure is to build a truth table. Because as much as they are not short, I think truth tables are simple. So, how many rows do I need for a truth table for either of these sentences? Because I've got 3 propositions, I double it each time. So 2, then 4, then 8. And in order to build it, the most on the right will flip every 1. The middle one will flip every 2. Helps if I write down the right letter. And then the leftmost one flips every 4. Double it every time. I should end up with 1 column for each of the logical operators I see. So in order to build this expression, P and Q in parentheses or R, I'm going to need 2 columns. I'm going to need a column for the parentheses, and then I'm going to need the or the R with that. And that's my left-hand side. That's the first expression. So, let's build some truth tables. Build some columns. This column only involves P and Q, which means, for the moment, I can ignore R. That's an and. How often is it true? How often is it false? It's only true when both are true. And that only happens, in this case, in the first 2 rows. Now I'm going to do the or R, yes? But I'm going to do this thing, or R, so I get to ignore the P column and the Q column. I only have to look at this column, or R. When is or true? When is or false? False if they're both false. It's true the rest of the time. This is the inclusive or, so I just need at least one of them, which means yes, 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 no. And then again, yes, no, yes, no. Okay, that's my left-hand side. Questions about how I got there? So, if there are no questions about this part, let's build the right side. The right side is going to be this piece, which means I start with Q or R. Start with the parentheses. And then I'll and a P outside of that. This will be my right-hand side. Again, I don't need to look at these anymore. They're not part of the game at the moment. I'm doing Q or R. Only two columns are active, the Q column and the R column.
True, 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 false. True, 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 false.
Because it's an or is only false if both of them are false. Now I need this column and P. Means I need my P column visible again. And is true when both are true. Yes, yes, yes. No. No. Wait a second. Yes, 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 no, yes. My left-hand side and my right-hand side are different. Even if I finish out the column, P here is a false, here is a false, here is a false. There are two different places where these don't match. If I were to do the if and only if part at the end here, left-hand side, if and only if, right-hand side, true, 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 bang, there's my problem. That last column needs to be all true to be a tautology. This is not a tautology. And that means what? This column, yes, this column is a contingency. What does that mean about my two statements? They're not logically equivalent. These two things don't mean the same thing. They actually tell different stories. Where I put the comma in my sentence in English, P and Q, comma, or R, P, comma, and Q or R. Okay, people, here's a very interesting application of how fine a detail this is. There was a lawsuit that went to the Supreme Court over pay for loading and shipping of trucks. And in the contract language, it said you were awarded pay at this rate for packaging, comma, transporting, comma, loading or shipping, no comma. That's the Oxford comma idea, right? So the people on the loading dock said they should be paid at the same rates as the shippers because loading or shipping is one thing. If that had gone through that way, it would have cost the trucking business over $150,000 a week. Guess what the Supreme Court ruled? The loaders were right. The lack of a comma made that one parenthetical expression with an or in it. And that meant something different. Whew. I would recommend, if you want to be amused on this, Google court case Oxford comma. You'll find the result. So, I did not use that giant table of logical equivalences. But I can when I am given something complicated. Now, I don't know who came up with this expression or why, or what sort of pain they're trying to inflict on me, but that's disgusting. Where would such a thing come up? The only thing I can figure out is that this is a bad electrician trying to do a switch job. And I need this switch here, and it's got to operate differently from this switch over here, and they need to work in this sort of, when are things on, when are things off? This looks nuts. So I grab my table, and I start looking at what things I can do. And I remember we just had De Morgan's law as one of our examples, which had a knot on the outside of a set of parentheses, right? So I see in the very left setup here a knot on the outside of a set of parentheses. Let's distribute that in. I distribute this here, that changes the negation, and flips the symbol in the middle. Now this table is on page 29. Y'all should have it up. Grab your book, grab your electronic copy, scroll to the right spot, find me this table, because now I'm looking at this and I'm trying to figure out what I can make easier here. What simplifying can I do? If it helps, think algebraically. Brandon? Aha! Right at the top of our table, I think it says double negation. So I'm going to say, by double negation, this is equivalent to P and not Q. Sorry, P or not Q, and P or Q. Oh, good. I've got fewer knots in my statement. I therefore think I have fewer mental knots in my thinking about this statement. I'm happy about that. Now what the hell do I do? Again, I like to think algebra here. Inside both set of parentheses, the first part of both set of parentheses is P or. P or thing, P or thing. Can I? Let's see if one of my rules allows me to do that. So I start digging, pull it out. What kind of a rule is that? That's undoing the idea of putting it in. What was the rule for putting it in called? Distributive rule. So let's look at our distributive rule. There's a distributive rule right here. And it says P or thing and P or thing. I can pull the P or out and I leave thing or thing. P or thing and P or thing. So by the distributive rule, I get P or thing and thing. Wait a second. Not Q and Q. I saw that earlier. It had a different letter on it. It said not P and P, right? Not only that, it was in the other order, yes? When we did that very back at the beginning of today's class, I wrote Shakespeare, P or not P, and then I wrote P and not P. So let me switch the order. In my table, it says the commutative rule. I can switch orders. And now I go back to the table and I look at the top couple of rules on the table. There's a bunch of stuff with capital T's and capital F's at the top of the table. And then there are a couple of things with capital T's and capital F's at the very bottom of the table, right? The two at the very bottom of the table, they say negation laws. And those negation laws are the tautology and the contradiction we came up with from Shakespeare. P or not P is always true. Let's just write a capital T. P and not P is always false. Let's just write a capital F. So I'm going to replace this with a capital F. Because that was our sentence that was a contradiction at the very beginning of class today. Now I look for rules that have a capital F in them. And there are only 3 of them. So there's a rule somewhere with a P or F. What's it say? So wait a minute. The truth of this thing, because that's an or is true when one of them is true, right? And this one's never going to be true, so I don't care about it. I only care about that. And that rule is labeled, what's that rule labeled? That rule is labeled identity. In other words, this big, ugly, complicated mother of a sentence is equivalent to just the letter T. Rip all of this ugly wiring out, replace it with one switch, you're done. I don't know about you, but electricians get paid by the hour. If I can fix this damn thing, then the next guy who comes out, oh, I just have to replace one switch. Thank you, I'm done. I charge you for the hour work because I was there, even just for a minute. I get paid for an hour. This sort of simplification for circuit design is actually used to make more and more complicated computer chips smaller and smaller and smaller and smaller by removing redundant pieces within the circuit. And if I can simplify this in my code, I can make my code faster because there's less code to work through. So I personally don't do a lot of this. But you all are the science people, the computer science people. I'm just a math geek in the corner. The other option would be if I gave you both of these and then asked you to show that this was equivalent. But in this case, I didn't. I just gave you one thing and said, make it nicer. In that case, this table is my best possible choice. Figuring out how to make these things simple. Am I going to expect you to have this table memorized? Hell no. Keep that bookmark somewhere. Please note that as I increase the number of letters involved, the number of rows in a truth table can get bigger and bigger and bigger. If I have as few as, I don't know, 7 propositions involved, 7 different letters, I'm looking at 128 rows. Do you think I'm going to want to try and do the truth table with 128 rows?
No.
I will probably go to this table first to try and make my life easier, to show logical equivalence. I would only go to a truth table like that if I had. I'm looking at over 1 million different rows. And every single logical operator, the knots, the ands, the ors, the arrows, all of those give me another column. So if I have 5 or 6 or 7 operators, I get 5 or 6 or 7 more columns. Oh boy. Is this anything other than tedium? Because really, it's the same 5 rules. Negation, and, or, if then, if and only if. Over and over and over and over again. Checking these sorts of things can be done automatically. It is possible to code this. And you do it with nothing more than switches and light bulbs. And you simplify it by flipping all the switches and looking at all the cases. It's exhausting, though. And so I don't want to do this if I don't have to. This is nicer, a little, rather than a giant truth table. But each situation you run into is going to give its own lean. Are you better off doing a truth table? Are you better off looking through this table of equivalences? It's going to depend on what information you're given to start with. Gavin, you said that this was a contingency in our example because it was sometimes true and sometimes false, right?
Yeah.
I want to think of this the same way I think of our system specifications. I want to know if a set of propositions is satisfiable. Here's a new definition for us. A set of propositions is satisfiable if some collection of truth values for the individual variables results in all of them being true. This is exactly what we did with our system specifications. Can I make the router can communicate with the addresses, send the packets, that problem number 11, that's the handout on our Canvas page. Eventually did a truth table and said, hey, look, here in this row, I got all of them to be true at the same time. That satisfies my propositions. So instead of simply saying this is contingent, quite frequently there are cases, I don't want to know, is it always true, but is it ever all true? And that's a different setting. A notation, those of you who took calculus, we talked about sums, right? And we talked about a sum like that, and that adds up the things number 1, number 2, number 3, number 4, I can and a bunch of propositions. That's P1 and P2 and all the way up to Pn. I can or a bunch of propositions the same way. De Morgan's rules work here. If I have a negation of a giant and, that is an or on the inside. When I distribute, I change all the ands to ors. That's De Morgan's rule, just instead of being on 2 things, it's on however many things I want. Please notice, all the things have to be the same. They're either all ands, all ors. These are written on page 31. We'll see you all on Friday. Have a wonderful rest of your day. If you came in late, please come give me your homework.